Does everyone kind of follow my reasoning there? Okay, as soon as it says friction is not a factor, there's no other non-conservative forces that could do any work. The only thing that pulls it down the ramp is gravity. And all gravity can do is change gravitational potential energy into kinetic energy, and it'll do it perfectly. Okay? Since there's no non-conservative forces, energy is conserved, and this becomes a question like what we would have looked at yesterday. All right? So it should really only be out of 1 mark, because the answer is 0. No work is done. This would happen, and all of the energy would be converted. Okay. Now, number 2, on the other hand, this one does require a little bit of work. Okay, we have a truck traveling at 14 meters per second, so we know its initial velocity, or speed in this case. It has a mass of 1,300 kilograms. The driver slams on the brakes and skids to a stop. How much work is done in stopping the truck? Okay, so we also know our final speed, because it says it comes to a stop. All right. What kind of energy is changing here? The kinetic energy is changing, and that's it. It never mentions anything about a change in height, so I have to assume that there's no change in potential energy. So the work done is the change in mechanical energy, but in this case, it's just the change in kinetic energy. Right? So that's going to mean that the work equals the final kinetic energy, EKF, minus the initial kinetic energy. Well, what's my final kinetic energy? 0. Okay, so my work is going to be 0 minus 1/2 times 1,300 kilograms times 14.5 squared. This is, after all, the initial kinetic energy is what I have to get rid of. If I'm slamming on the brakes, I want to turn that energy into heat and sound and anything but me moving forward. Okay? So when I do that, I'm going to get a negative number. Is it okay for me to get a negative number for work?
Yeah.
Yeah, it's energy lost by the truck. Okay, so it should end up being a negative number. Right? It doesn't mean it's backwards or forwards, it just means it's energy lost by the truck. So we would have 0 minus 0.5 times 1,300 times 14.5 squared. All right, so we would be looking at, we have 3 significant digits there, so negative 1.37 times 10 to the 5 joules. Okay, that would be my answer for that one. Okay. Is that a pretty straightforward work energy theorem problem?
Yeah.
Yeah, it is. Okay, and honestly, I didn't make the one on your test much harder than that. All right, let's have a look at the conservation of energy stuff from yesterday. So we were working on this model rocket question at the end of class yesterday. Okay, so the model rocket is fired, okay, and while the engine is firing, work is being done, and it's changing the mechanical energy of the rocket. The question begins when the propellant runs out. Okay, so that now the rocket is out of fuel, and it's 220 meters above the ground, moving at 165 meters per second. All right, so we know our VI, 165 meters per second. I think we did this first part. So, okay, and the initial height was 220 meters. All right, if I want to calculate the mechanical energy, that's pretty straightforward. Mechanical energy is the sum of an object's potential energy and its kinetic energy. All right, so all I have to do is go 3 kilograms times 9.81 times 220 plus 1/2 times 3 times 165 squared. Okay, and I think that came out to 4.73, yeah, times 10 to the 4 joules. Okay, so that's the mechanical energy where?
Everywhere.
Everywhere. Okay, from that point on, that is the mechanical energy of the rocket. Right? Now, that's important for me to remember because in part B, they ask when it reaches its highest point, and remember, this rocket was shot straight up in the air. When it reaches its highest point, Okay, what will its gravitational potential energy be? Well, at its highest point, how fast is it going? 0. So all of its energy would be potential. So how much would that be? 4.73 times 10 to the 4. It's just us recognizing, oh right, when it goes up in the air, if it's going straight up at its highest point, it doesn't have any kinetic energy because it's not moving, okay? And just recognize that, okay? How far above the ground is the rocket at its highest point? Well, I would just set this number then equal to its potential energy at that point because that's all it would have. Is everyone okay with that? All right, so I would simply say then that 4.73 times 10 to the 4 joules equals 3 times 9.81 times its highest point. Just divide both sides by 3 times 9.81. And I'll have that final height, okay? And okay, so 4.73 divided by 3 times 9.81. Okay, so it will be at 1,607 meters. We only have 3 significant digits, so 1.61 times 10 to the 3 meters. That's 1 mile. Okay, that would be a height of 1 mile, 1,600 meters. Okay. All right, when it hits the ground, what is its speed? How much energy does it have when it hits the ground? 4.73 times 10 to the 4 joules. All of it is kinetic. All right, so it's basically the same idea. Okay, we would say, all right, 4.73 times 10 to the 4 equals 1/2 times 3 times VF squared. So we just divide both sides by 1.5 and square root it. Okay, and we'll have our VF All right, we're moving at 178 meters per second when it hits the ground. Okay? Everybody all right with that? Does that make sense? Those are pretty basic law of conservation of energy problems, really, when it comes right down to it. Okay? The big thing here is, again, not the math. It's the recognition of, all right, when it's in this position, here's how the law of conservation of energy applies. When it's in this position, here's how it applies. And just being able to do that, okay, in a new situation. Okay, I would like you guys to try 3 and 4. They're both law of conservation of energy questions. Let's see how we do with those. And if we're doing okay with those, then we'll move on to look at power after that. Because again, this is review of Science 10. These are, you know what, let's just do 4 and see how 4 goes. Okay, now we are going to say that for number 4, there's no horizontal component to her movement. She's just going to go straight up, which in pole vault would be a disaster. Okay, because you don't want to go straight up because then you'll come straight back down and there's no pad there. Okay, but we're just going to say that for simplicity's sake. All right, let's look at part A here, okay, which is just the law of conservation of energy part. Then I'm going to show you some videos of the greatest pole vaulter who ever lived, okay, before we do part B, because you have to kind of, if you've never seen pole vault, you have to kind of see pole vault happen in order to get an idea of what the energy changes look like during the pole vaulting process. Incidentally, the greatest pole vaulter ever was Sergei Bubka, okay, who was a Russian pole vaulter, okay, who just like smashed records every single time he picked up a pole. Okay, like he was just sick. So what we're going to look at here, okay, is our 56 kilogram pole vaulter. Okay, so we know the mass, not that it's going to matter, but we have it, 56 kilograms. We know the initial speed of the pole vaulter to be 8.00 meters per second, and we know the initial height, because we do have to treat this from the center of mass, okay? We can't say that her whole mass is on the ground, only her feet are on the ground. Her center of mass, most of her mass is above the ground, okay, a little bit. So she could fall, which means and sometimes people do in pole vault, okay, she could fall, and that would mean that most of her mass could still lower its height down to the ground, okay? So we're going to assume that her initial height is 0.850 meters above the ground. So we are going to figure out what her maximum height could be, okay, if we're converting all of her approach energy into height, okay? So that means there's no change in energy, okay? So that's going to mean that EI equals EF. Right? We're going to convert the small amount of potential energy she has on the ground, okay, and all of the kinetic energy, which is considerable, she's running at 8 meters per second, okay, into only what kind of energy? Only potential. All right, so our initial energy will be both, so we'll have m times g times h initial plus 1/2 mv initial squared equals m times g times h final. All right, so we can cancel the masses right now. Mass is in every term, okay, so we can get rid of it. We're just looking for HF, so all we have to do is divide both sides by G, and we're there. Okay, so the algebra for this one's pretty straightforward. So we'll have 9.81 times 0.85, her initial height, plus 1/2 times 8 squared, okay, divided by 9.81. All right, so when we do that, we should get 4.11 meters, which I can tell you, okay, for women's pole vault is an incredibly respectable number. Okay? I coached track and field for over 20 years, and I can count on one hand the number of times I saw any high school athlete go over 3 meters. Okay, so this is considerable. 4.11 meters is pretty high. Now, Sergei Bubka, on the other hand, guy's a machine. Okay, he can really go. All right, sorry for you guys at home. I can't show this because I just Google Sergei Bubka on YouTube. If we could see in that video, there's quite a few energy conversions that go on. Okay, there's obviously the portion of the pole vault where work is done, and that is where the athlete is running down the track, building up mechanical energy in the form of kinetic energy. Okay, then you can see that as they approach, so as they're running, the pole is positioned like this, okay, and they're running like this, and then as they approach the box, which is this small box in the ground that you would put the pole in, okay, they convert and they bring the pole over and they plant the pole in the box. Okay, at that point, what starts happening to the pole? Right. They're doing work now on the pole. They're taking the kinetic energy that they've built up and they are using it to do work on the pole. They're exerting a force over a distance, bending the pole. Okay, they're turning their kinetic energy into elastic potential energy in the pole. Okay, now, interesting thing about pole vault poles. Okay, they have a soft side and a hard side. One side will bend and the other won't. That's what makes them fling you up over the bar. If that rotates in your hand while you're planting and you have it sideways or upside down, it will snap under load. Okay, and I've seen that happen a number of times, okay, where somebody's hands got a little bit sweaty, and as they planted the pole, their hands shifted on the pole didn't shift, okay, and as soon as they got committed, that means their feet were up and their head was down, that's where the pole explodes, okay, so you have to be mindful of that. In this case, this guy knows exactly what he's doing, and when you watch him go up and over the pole, it is almost perfectly vertical. He wastes none of the energy on a horizontal part, just enough to clear the bar. Okay? He's also, his core strength, and this is really important for all pole vaulters, to have just incredible core strength. When that pole is now straight and they're above it, they need to be able to push on that pole while staying inverted. That's what gives them that extra little bit of lift. Okay? The pole is only 4.5 meters long or 5 meters long. He's got to get that extra meter over the bar, okay, in that case. So there's a lot of energy conversions that go on. So that pole, once it's bent completely, then starts to do work on the athlete, pushing them up, elevating them into the air. Okay? So you've got that energy conversion as well. Then you get to your maximum height where all of your energy is potential, and then that potential turns back into kinetic as you fall down into the pit. Okay? So there's a lot of energy conversions that go on in the process of doing a pole vault properly. Okay, making sense? Okay, how are we feeling about the law of conservation of energy problems? Okay, do we want to do a couple more? Okay. One more? Okay.
Give us a hard look.
That's what I'm looking for. Okay, no, come on, I gotta have one no, let's go with that one. Let's go with the roller coaster. Okay, so we got a roller coaster, and this part makes it a little bit easier. It starts from rest, okay, at the top of a 12-meter high hill. What will the speed of the roller coaster be when it is 4 meters above the ground on a frictionless track? You can. So, since they tell us that the roller coaster is frictionless, that means there's no work being done. Okay, it doesn't tell us that there's a motor pushing the thing faster or anything like that. This is a law of conservation of energy question where EI equals EF. Okay, some of the pieces of information we're given, VI is 0 meters per second, HI is 12 meters, so this is like a smaller roller coaster. Okay, and we're looking for the speed of the roller coaster when it is only 4 meters above the ground, so we're looking for VF. Okay, so we could say here then that initial potential plus initial kinetic equals final potential plus final kinetic. Are any of those 0 given the context of the question? Initial kinetic, right, because they say right here, you're starting from rest. If I'm starting from rest, I can't have any of that. All right, what I'm looking for is VF, which is part of my final kinetic energy. So I want to isolate final kinetic energy right now. What should I do with my final potential energy? Subtract it over. All right, so I'm going to have my initial potential minus my final potential equals my final kinetic. Okay, now I can expand out. M times G times H initial minus M times G times H final equals 1/2 MV final squared. Mass can cancel, okay, which is good. I wasn't told what the mass of the roller coaster was anyway. Okay, now I want to isolate VF, so I divide both sides by 1/2 and then I square root. That'll give me VF. So when I'm plugging in my numbers, I'm going to have 9.81 times 12 minus 9.81 times 4, or you could have just gone 9.81 times 8. Okay, that would have worked too. Right? Then divide that by 1/2 and square root it. Okay, so square root of 9.81 times 8. No, forget it, I did that wrong. Well, I'll just write it the way I have it. 9.81 times 12 minus 9.81 times 4. Okay, divided by 1/2 and then square rooted. All right, so the roller coaster will have accelerated to 13 meters per second over that change in height. Okay? Yeah, it's a little kiddie roller coaster. It's not like the Mind Bender or something like that. Okay? It's something quite a bit more tame. Okay, now, here's a different situation. Let me pose this question to you. Which would have more total mechanical energy? A rock, let's say a 5-kilogram rock dropped from a helicopter that is hovering in place 200 meters above the ground, or an identical 5-kilogram rock dropped from a plane that's the same height but moving at 200 meters per second. The plane. Why?
Because you start with the kinetic.
Right. I start with kinetic energy. Does it matter that that energy or that velocity is horizontal? It doesn't. Okay. Remember that energy is scaling. All right. So I could actually make the rock in the helicopter have the same amount of mechanical energy by throwing it downwards at the same speed that the plane would have. Okay? Would it matter that I threw it downwards and the plane dropped it horizontally? It doesn't. Again, energy is scalar. That rock has energy because it is moving at a certain speed. The direction makes no difference. Okay? Does that sort of make sense to everybody? You know, just in case maybe that's a hint for tomorrow. Well, actually, not tomorrow. I decided that in the interest of fairness, okay, since some people are not here today, okay, that I'm going to bump your exam until Monday. Here's why I have to bump it till Monday. We got to catch everybody up tomorrow. Thursday's classes are shortened because of the Remembrance Day service, and Friday is Remembrance Day. So lucky you got almost an extra week to study for this test that you didn't have before. Okay? Now, understand that I'm only going to take questions tomorrow for people that were not here. I'm recording that. Okay? But I'm not going to like reteach everything because there's not really much new here, okay, today. But in the interest of fairness, that gives everybody time to get caught up, okay, and not have to worry about the test being tomorrow. So now it will be Monday, okay, but we will probably get on to Unit 3, okay, at some point tomorrow, okay, and be in Unit 3 on Thursday. Okay, we won't be spending more time on Unit 2. Okay. All right, let's talk about power. That's our next thing. Yep. Yes, at 11. Yep. Okay, so I talked about power the other day, and I said it only takes me like 15 minutes to teach power. And then I told you everything you needed to know about power in 3 minutes. So what do I know? Okay, so I'm just going to quickly go over it again. Okay, all you need to know about power is basically what it is and how it might be applied in a real world situation. You will not have to do any problem solving to do with power. As long as you understand what power is, you're good, because there's only one multiple choice question on the test on Monday on power. Okay, so what is power? Power is the rate at which work is done. Okay, so it is possible for two machines with widely different power ratings to do the same amount of work. Okay, the difference is how quickly the machines will do that amount of work. They will both do that amount of work, but they will do it at different rates because power is work divided by time. Okay, so if I've got on the left a 1991 Honda Civic, okay, hatchback with a 1.6 liter twin cam engine capable of generating a whopping 118 horsepower, okay, and capable of going from 0 to 60 in about 2 weeks, okay, versus the Paul Walker Vin Diesel modified version of the same car, okay, which would run 600 horsepower because they throw like 3 turbos on it and then a bunch of intercoolers and, you know, cool air intake and big exhaust and whatever else they do that magically transforms an otherwise gutless wonder into this incredible racing machine. Okay, they can both get to 60 miles an hour, the same amount of work, but the Fast and Furious model can do it a lot faster because it's simply more powerful, okay? More horsepower. Does that make sense to everybody? Okay, so if I had a 1,000 watt hair dryer and a 1,500 watt hair dryer, which one dries my hair faster? Thanks, you guys are kind. Nobody said you don't have enough hair for it to matter. Okay, so yeah, the 1,500 one is going to do it faster because it's simply more powerful. Okay, the units for power, guys, are watts. Okay, and the reason they're watts is because, like we said, power is work divided by time. That's joules per second. That is a watt. Okay, a joule per second is a watt. So when you read something's power rating, it's basically telling you how much energy it will consume or how much work it is capable of doing in 1 second. Can these two devices do the same amount of work? Yep. Okay? They can both generate electricity using the power of falling water. Grand Coulee Dam there on the right, okay, versus the little water wheel. If I ran Grand Coulee Dam for 1 second and the little water wheel for 1,000 years, yes, they could probably do the same amount of work. Okay? After all, the Grand Coulee Dam powers much of the Pacific Northwest. That would be like Spokane, Seattle, parts of Oregon. It's kind of a big deal, okay, in terms of making electricity, whereas that water wheel would be hard-pressed to run a 100-watt light bulb, okay, on its own. Okay, so as we were saying, power is work divided by time, which can also be force times distance over time, which can also be force times velocity. Again, you're not going to have to do any calculating, it's just that you understand that there's multiple ways to calculate it. Okay? All right. Just because people usually ask, I always put this up here, because I don't understand watts as a power unit unless it's something small, like a microwave or a hairdryer, then it kind of makes sense to me. Okay? But when it starts getting into cars, okay, like if I go and I look at a Tesla and it tells me that it's like 20 kilowatts, I'm like, is that good? Is that a lot? Because I don't really know. Okay, when it comes to cars or engines, I kind of need horsepower to know. Okay, is 20 kilowatts like my blender, or is it a lot, like, you know, a Lamborghini? Like, I don't know. So it's kind of hard to figure that out. So here's your conversion. 1 horsepower is 746 watts. Okay, 20 kilowatts is 20,000 watts. Okay, so if we take 20,000 and divide it by 746, okay, that's a 26 horsepower motor. No thanks. I want to go faster. Okay, that's simply not enough for me. I have no idea what the Tesla motors are. Okay, but the big thing here is that you could get an electric car with what would seem like a low horsepower rating, but you also have to remember that all of it goes to the road. None of it is lost to friction and heat, because an electric motor is far more efficient than a gas motor. Okay, so even though a 700 horsepower car might look very impressive while it obliterates its tires and screens and, you know, all that kind of stuff, it's probably still not going to be as fast as something that's a bit more efficient. Okay? Everybody with me on that? Okay. So we'll skip over that because we don't have to do any calculating. And we're going to go to this. Okay? We are going to figure out how much horsepower Yoda would be capable of generating, because it's fun. Okay? So, there was this comic book a while back that was doing this examination of the ethical problem with having Superman turn a giant wheel to generate enough electricity, free electricity for the entire world. Okay? They were examining whether that was ethical or not. Like, would enslaving Superman to doing this be something you could do? And then they were looking at the practicality of it. How fast would Superman need to go in order to do all this? But he reversed the spin of the Earth, because that's a thing. Okay, yeah. So they were kind of looking at that. So we altered it a little bit, and we're looking at Yoda instead. Okay, so we're wondering if we put Yoda down at like Pincher Creek, okay, and run the wind turbines, right? We want to see how much he can do. So we put little Yoda down next to all the wind turbines, and he looks up and he goes, rotate your wheel, and makes them go, okay? Then we can see how much force power would be possible there, okay? So what we're going to do is we're going to use some information gathered by someone far nerdier than me, if you can imagine such a thing, okay? They've gathered some information from various bits and pieces of the original trilogy, which of course we all know is the best trilogy, okay, in terms of figuring this out. So the first thing I got to do is I got to show you the video, okay, that goes along with this, which is the most important scene in all of Star Wars. Okay? It is the scene in which Yoda explains the nature of the Force to Luke Skywalker. Okay? It is the first time it is ever explained to anybody. And it occurs in the best movie ever made. The Empire Strikes Back. If you don't agree with me, you're wrong. Okay? It's the best movie ever made. Okay? And it just is. So we're going to watch this because not only is it good like for physics part, but it's also kind of one of those things that talks about things bigger than ourselves, ideas bigger than ourselves, right? This idea of faith can move mountains kind of an idea. Luke doesn't believe that he can do this thing, and Yoda shows him, well, it's because that's why you fail. You don't believe you can do it, okay? You don't have any faith, okay? Faith can do incredible things if you have it, is kind of the analogy here, okay? So, for those of you that are watching this at home, I'll post a link to the video in Google Classroom. If we're looking at this example now, okay? We know that the energy it takes to lift an object to a certain height is equal to what three things multiplied together?
Mass, gravity, starting height.
Right, mass, gravity, and starting, and the height that we lift it to, assuming it's from the ground. Okay, so we know it's mass, okay, times gravity, okay, times height. Okay, now, the X-Wing scene, okay, lets us figure out how powerful Yoda is. He lifts the starfighter right out of the swamp, which Luke couldn't do. And then in The Rise of Skywalker, which is like the second biggest travesty in the entire Star Wars saga, okay, he gets vindicated by pulling it out of the water on Octo. Okay, but yeah, it's too little too late by then. Okay, all right. So, first thing we need to know is how heavy the ship was. An X-Wing's mass has never been canonically established. That means Disney hasn't told us how much it weighs at any point. So we'll have to approximate a little bit. Okay? Its length, however, is in canon for some reason. It's 12.5 meters long. Okay? An F-22, which is a real aircraft fighter jet, okay, weighs 19,700 kilograms. So if we go down from this, we could say an X-Wing has a mass of about 12,000, we should say, kilograms. Okay, so now we've got a mass that we're going to use for the mass of the X-Wing. Okay, next we need to know how fast it was rising. Sorry, 5,600 kilograms. Sorry, 5,600 kilograms. So we need to figure out how fast it's rising. Thankfully, someone far nerdier than me took the time to time it rising out of the swamp. Right? So what he did is he watched that the front landing strut rises out of the water in about 3.5 seconds. Okay? And he estimated the strut to be 1.4 meters long. And the way he did that was he went back to episode 4, A New Hope, where there's a scene of a mechanic bending down to walk underneath an X-Wing, giving him an approximate height for the landing strut. Like I say, on the level of nerd, I'm not at the top. Okay? There are people higher up than me. Okay? So, if we know that, okay, we know that it's 1.4 meters long, and it took 3.5 seconds, we can simply go V equals D over T, and that'll tell us how fast the X-Wing was being lifted out of the ground. Okay, so we would just take our 1.4 meters and divide it by the 3.5 seconds, okay, and we'll have the speed at which it's moving. So 1.4 divided by 3.5. All right, so that means it's moving at 0.4 meters per second. Lastly, we need to know the strength of gravity on Dagobah, because this scene does not occur on Earth. It occurs on an imaginary planet called Dagobah. And we have to know what the acceleration due to gravity is there. Okay? Now, here we figure we're probably stuck, because while sci-fi fans are obsessive, it's not like there's going to be a catalog of minor geophysical characteristics for every planet visited in the Star Wars universe. Except there is. And it's called Wikipedia. It's a thing. I kid you not. Okay? So, you go to Wikipedia and you can actually find what the acceleration due to gravity on basically any planet ever visited in Star Wars would be. And in this case, it is 0.9 g. That means 90% of Earth's gravity. So, G on Dagobah will be 0.9 times 9.81. So 8.829 meters per second squared. So now all the crap that Luke did, flipping over and lifting rocks and stuff, doesn't seem quite as impressive. I mean, I could jump 10% higher on Dagobah if I wanted. So I could actually like get over top of the credit card. All right, so if we want to figure this out, okay, so we can now calculate the peak power output because we have the lift rate, okay, we've got all of this stuff. So, okay, if I want to calculate how much power there is, power is work divided by time, okay, so I can take either the force and multiply it by the velocity, or I can go force times distance and divide it by time. Either way will work, okay, to calculate his overall power output. So to calculate the force, it's just the force of gravity. That's all he's working against here. We're not going to count that there were weeds stuck to the ship and that there was probably stuck in the mud and that would have made it harder to lift. We're just going to say he's working against gravity. Okay, so we're going to take that 5,600 kilograms times our acceleration due to gravity, okay, and then we're going to multiply that by 0.4 meters per second. Okay, so 19,776 watts. That's 20 kilowatts. 20 kilowatts worth of power. Okay, so that's about 25 horsepower, or about the power of a motor in an electric model smart car. It's certainly not going to generate enough electricity, okay, to feed the world's electricity stuff. Okay, so Yoda would be worth about $2 an hour, which is like slave labor equivalent. Okay, so we have to remember, of course, that in Star Wars, there's only telekinesis is only one example of the things that people can do. They can also apparently shoot electrical bolts of lightning out of their fingertips when angered. Okay, to do that, you require millions of watts usually if you're going to arc it over any distance for any length of time. Okay, it could easily be in the megawatts. Okay, that's like what an arc welder is. If you've ever seen someone with a welding truck, okay, they've got a giant generator on the back to make enough electricity to run it. Okay, so it's kind of a big deal to generate that kind of electricity. Okay, so when it comes right down to it, it would be difficult to power everything with Yoda, but it'd be green. Yeah, terrible, terrible. Okay, so yeah, definitely it's not going to work, but it's just kind of a fun little exercise for us there. Okay, we got what, about 15 minutes left in class? No, sorry, we have like 8 minutes left in class here. So your test has been moved to Monday. We're going to start Unit 3 tomorrow. Work on Unit 3 on Thursday. Okay, but I'll take any questions that people have about law of conservation of energy. Maybe we'll start class with a couple of law of conservation of energy problems tomorrow just to review. Okay, power is, we're done power. Okay, we don't need to know much more about it than what we've already done. And then we'll start Unit 3, do Unit 3 on Thursday, okay, and then your exam will be Monday. Right, that gives you a little extra time to come in and see me if you need some help on anything. Okay, so take advantage of the grace period there. Okay, so remainder of class, I would say not a bad idea to work on the review package. See if any questions come up. Okay.